Welcome to my lecture on the central limit theorem. Before I get started, I want to remind you of Theorem 4.4.3, which states the following. It says if x is normal with mean mu and standard deviation sigma, then z, which is just going to be x minus mu over sigma, is a standard normal. Okay, and standard normal just means this. It means that the mean is 0 and standard deviation is 1. Okay, so now let's get on to the statement of the central limit theorem. Okay, so central limit theorem says this. Okay, if x1 through xn are independent, meaning one observation does not affect the other, and identically distributed, which has the meaning that the same experimental process is repeated on the observations for practical purposes, then the average, which is just this x1 plus x2 plus x sub n divided by n, is also normally distributed. Okay. And if it has a normal distribution, we need to specify the parameters. So with mean mu and standard deviation, sigma over root n. Now I'm going to do something just a little bit different here, and this is optional. I'm going to put a subscript of an x here, and I'm going to state what these mean. So where mu sub x is the mean of the observate, is the mean of let me just erase that, is the mean of x sub I and sigma sub x is the variance. Excuse me. Let me do sigma squared sub x is the variance of x sub I, the individual observations. So mu sub x is the mean of one single observation x sub I, and sigma sub x is the standard deviation of an individual x sub I, equivalently sigma squared of x, the variance of x sub I. Okay. Now let's get on with the statement, and I'm going to prove it in a very special case. By the way, I'm going to abbreviate central limit theorem by CLT from here on out. Okay, so here's going to be a proof, and this is going to be when each observation x sub I is normal with mean mu and variance sigma squared. Now you could put in the sub x there if you like, but I'm going to leave them off. The sub x just means that it pertains to the observation x sub I. Okay. So I'm going to let y equal to x bar. And x bar is going to be x1 plus x2 plus x sub n when we add everything up. So I need some dots here. Divided by n. So this is going to be 1 over n times x1 plus 1 over n times x sub n. Okay? So I should say let that define y. Then we're going to calculate the moment generating function of y. M sub y of t is going to be equal to, well, I'm going to use theorem 7.3.2, and this is going to boil down to the moment generating function of 1 over n times x sub 1 of t times the moment generating function of 1 over n times x sub 2 of t times the moment generating function of 1 over n times x sub n of t. Okay. And we know the moment generating function of each of these, but there's one more piece to use here. Because these x sub i's are being multiplied by 1 over n, we're going to use Theorem 7.3.3. And it's going to state the following. It's going to state that the moment generating function of this first piece, x sub 1, is going to be 1 over n times t times the moment generating function of x2 of 1 over n times t. And we keep multiplying. Now, 1 over n times t is the same as t over n. So I can just write it like that. And thus, by Theorem 7.3.3, then the moment generating function of a normal with mean mu and variance sigma squared is going to be e to the mu t plus sigma squared times t squared over 2. Okay, and we're just going to use that right here. This comes from page 136. So by page 136, I'm going to plug in the moment generating function for x1. But now remember, I have to compose it by this 1 over n times t. So it's going to be e to the mu times, instead of having t, I'm going to have t over n plus sigma squared times t over n squared over 2. Now I'm going to repeat that for x2 because it's exactly the same distribution. Okay, and that's what I get when I simplify it. Then this is going to be repeated until I get to the last term. And now I'm going to simplify just by doing algebra. And this is going to be e to the mu times t over n, plus from the next term, this is going to be mu times the t over n. That's going to keep happening n times. Then I'm going to add the portion that corresponds to the t squared. So it's going to be sigma squared over n squared times t squared over 2 plus sigma squared times t squared. That'll be over n squared divided by 2 and then just more algebra will simplify. And we're going to get from this piece right here, since we're adding the n times, we're going to get mu times t. From this piece right here, since we're adding the same thing n times, I'm going to get sigma squared over n times t squared over 2. Now remember that by theorem 7.3.1, this is the moment generating function of a normal distribution. So by theorem 7.3.1, y, which is x bar, has a normal distribution with mean, well, the mean here is multiplied by the t term, so the mean is mu, and it appears as mu times t, so it is mu, with mean mu, and variance. The variance is going to be multiplied by t squared over 2, which is sigma over root n. So its variance is going to be sigma squared over n, not root n. Hence, standard deviation is the square root of that. So we'll get sigma over root n. Okay. So the statement of the central limit theorem says, as long as I have a bunch of independent and identically distributed random variables, the average is normally distributed with mean mu and variance sigma squared over root n. All right, well, that's the lecture on the central limit theorem. It is very important, and I hope you found it useful. Thank you.